A separator can be pressure rated, code compliant, fully inspected, painted, tagged, and mechanically complete, and still fail the moment the real process enters it. That is the first truth you need to understand. An oil and gas separator is not simply a pressure vessel with an inlet, a gas outlet, and a liquid outlet. It is a dynamic process system where momentum, gravity, retention time, droplet behavior, pressure, temperature, level control, corrosion, solids, foam, slugging, instrumentation, and operator response all meet inside one vessel. When any one of those elements is misunderstood, the separator may remain mechanically intact while the process quietly collapses around it. You see liquid carryover into the gas line. You see gas blow-by into the liquid system. You see unstable level control. You see mist extractor flooding. You see poor oil-water separation. You see compressor trips. You see contaminated downstream equipment. You see production restrictions. You see repeated alarms that operators eventually begin to treat as normal. None of those conditions are normal. They are evidence that the separator was sized as equipment but not designed as a system. So when somebody asks, is the separator correctly sized? I want you to ask a better question. Sized for which case? For maximum gas flow or minimum pressure? For normal liquid flow or maximum slug volume? For clean liquid or foaming crude? For initial production or end of field life conditions? For stable two-phase flow or intermittent three-phase flow? For theoretical separation or actual operating behavior? That is where real engineering begins. The first function of a separator is primary separation. The incoming multi-phase stream may arrive with substantial velocity and momentum. If that momentum is not controlled immediately, the vessel becomes turbulent, the liquid is re-entrained, the mist extractor is overloaded, and the level system becomes unstable. The inlet device must reduce momentum, change flow direction, and remove bulk liquid from gas. But more complexity does not automatically mean better design. A sophisticated inlet device may create better initial separation, but it may also create pressure drop, fouling, erosion, plugging, maintenance difficulty, and sensitivity to wax or solids. The correct device is not the most advanced device. It is the device that performs across the real operating envelope without becoming the next failure point. After primary separation, the gas moves into the secondary separation zone. Here, gravity must be given enough space and time to remove remaining droplets. The basic logic is simple. The gas velocity must remain low enough for liquid droplets to fall out rather than remain entrained. But do not let a simple equation deceive you into thinking the physics is simple. Gas capacity depends on gas density, liquid density, droplet size, turbulence, pressure, temperature, geometry, internal arrangement, foaming, liquid loading, and the actual condition of the mist extractor. You may calculate an allowable velocity to 3 decimal places, while your uncertainty in droplet behavior is far greater than the precision shown on the spreadsheet. That is why engineering judgment matters. A separator that works well at one pressure may fail at another because gas volumetric flow changes with pressure. At lower pressure, the same mass flow occupies more volume. This means the controlling gas capacity case may occur at minimum pressure, not maximum pressure. If you size only at one convenient operating condition, you may be designing around the wrong case. Now consider the liquid section. Many calculations reduce liquid capacity to flow multiplied by retention time. The arithmetic is correct, but the engineering question is still unanswered. Why is that retention time required? Is it to release gas from oil? Is it to absorb incoming liquid surges? Is it to separate oil from water? Is it to stabilize level measurement? Is it to prevent gas blow-by? Is it to provide time for operator response? Residence time is not a ritual number copied from an old datasheet. It's a process requirement that must reflect density, viscosity, temperature, droplet size, emulsion tendency, foam, solids, and fluid behavior. A 1-minute retention time may be adequate in one light condensate service and completely inadequate in another heavy, viscous, or foaming service. If you cannot explain what the liquid volume is achieving, then you have not justified it. 3-phase separation makes the problem more demanding because the vessel must solve 2 different separation mechanisms at the same time. It must separate gas from liquid, and it must separate oil from water. Gas-liquid separation depends strongly on gas velocity and droplet disengagement. Oil-water separation depends on density difference, viscosity, droplet size, emulsion stability, and settling time. The vessel drawing may show a clean, sharp interface between oil and water, but the real process may contain foam, solids, chemicals, and a broad emulsion layer. Your interface instrument is not measuring a perfect boundary. It may be trying to interpret a changing transition zone. This is why instrumentation cannot be treated as an afterthought. The instrument technology, nozzle location, measurement range, and control philosophy must reflect the real fluid. A separator can be generously sized and still fail because the interface measurement is wrong. Poor interface control causes water in oil, oil in produced water, unstable outlet valves, high-level trips, low-level trips, and downstream overload. You cannot solve that by simply increasing vessel volume. Foaming creates another level of difficulty. Foam consumes gas disengagement space, distorts level measurements, destabilizes control, overloads mist extractors, and reduces throughput. A separator that looks adequate on a clean fluid calculation may become effectively undersized when foam occupies the available volume. You must understand the source of the foam. Is it fluid chemistry, inlet shear, pressure drop, temperature, chemical treatment, poor inlet device selection? Foam is not an operational inconvenience that design can ignore. It is a process condition that must be addressed early. Then comes slug flow. This is where steady-state design assumptions are exposed. A separator may easily handle the average liquid flow and still fail when a large slug arrives over 30 seconds. You need to understand the slug volume, arrival duration, frequency, level rise, gas displacement, available surge space, control valve response, and downstream capacity. The vessel should not only contain the slug, it must recover from it. If the separator receives a slug safely but then dumps the entire accumulated volume downstream faster than the next system can handle, you have not solved the problem. You have moved it. The mist extractor is the final defense against liquid carryover. Its purpose is to coalesce small droplets and remove them before gas leaves the vessel. But the mist extractor is also one of the most vulnerable internal components. It may flood, foul, corrode, collapse, plug, drain poorly, or operate above its intended gas velocity. A mist extractor cannot rescue poor upstream separation. If the inlet section creates excessive liquid loading, if the gas velocity is too high, or if foam fills the vessel, the mist extractor becomes the last overloaded barrier rather than an effective separation device. You must specify the performance you actually need. What droplet size must be removed, at what gas velocity, at what liquid loading, with what pressure drop, across what turndown, under what fouling conditions. Provide suitable mist extractor is not a complete specification. Now look at level control. The liquid level is the operating heart of the separator. If the level rises too high, you lose gas disengagement volume and risk liquid carryover. If the level falls too low, you risk gas blow-by through the liquid outlet. Both events can become serious. Gas blow-by may overpressure downstream equipment, disturb pumps, create flashing, vibration, and unsafe conditions. The normal control level, alarm levels, and shutdown levels must therefore be selected from process consequences, not arbitrary percentages of transmitter span. You need to ask how much time exists between high level and high level. How quickly can the upstream source be isolated? How fast can the outlet system respond? Is the control valve oversized? Is the measurement stable in foam or emulsion? Can the operator verify the reading? Good level control is not merely tuning a controller. It is vessel volume, measurement, valve sizing, nozzle location, process dynamics, and protection working together. Pressure control matters equally because operating pressure affects gas density, gas volumetric flow, flashing, and separator capacity. A hunting pressure controller can create unstable separation even when the vessel is otherwise adequate. Pressure control valve sizing, downstream pressure variation, compressor interaction, available pressure drop, noise, vibration, and fail position all influence performance. Control and protection must also be kept separate. A normal controller is designed to regulate operation. It should not automatically be assumed to provide all protective functions. Depending on the consequences, independent, high level, low level, or high pressure shutdown functions may be required. The logic must follow the risk. If high liquid level can damage a compressor, contaminate downstream treatment, or create pipeline liquid accumulation, then the protection philosophy must be explicit. If low liquid level can send gas into a lower pressure liquid system, The downstream equipment must be protected. A separator is not merely controlled equipment. In many plants, it is part of the process safety barrier system. The pressure relief philosophy must also be based on credible scenarios: blocked gas outlet, upstream high-pressure source, control failure, fire exposure, gas blow-by, thermal expansion, and other applicable cases must be assessed. The relief device is not the entire solution. You must also consider discharge piping, flare header pressure, back pressure, reaction forces, drainage, two-phase flow, and final disposal. A pressure vessel can be mechanically strong and still be poorly protected. Corrosion brings another layer of risk. Water, carbon dioxide, hydrogen sulfide, oxygen chlorides, organic acids, solids, and deposits can all influence degradation. Corrosion is not determined by one fluid concentration. It depends on temperature, partial pressure, wetting, velocity, material, stress, surface condition, deposits, and time. Corrosion allowance may be part of the strategy, but it is not always enough. Localized corrosion under deposits can penetrate rapidly, while the average wall thickness still appears acceptable. Material selection, internal coating, chemical inhibition, monitoring, inspection, and cleaning must be matched to the actual mechanism. Internal coatings may help, but they are engineered systems, not decorative paint. They require correct surface preparation, application quality, inspection, compatibility, and repair philosophy. Sand, scale, and solids must also be considered. They can erode internals, plug drains, damage control valves, interfere with level instruments, reduce effective vessel volume, and create corrosion under deposits. You must know where solids will settle and how they will be removed. Wax, paraffin, and hydrates can foul mist extractors, block nozzles, distort level measurements, and make maintenance difficult. A compact separator is not efficient if it cannot be cleaned. Fabrication, inspection, and testing remain essential, but you must understand their limits. A hydrostatic test demonstrates pressure boundary integrity under defined conditions. It does not prove separation performance. A vessel may pass every mechanical inspection and still perform badly because the process design, internals, or controls are wrong. The separator datasheet is therefore more than a procurement form. It is the technical contract between process intent and equipment supply. It should define flows, densities, viscosity, gas properties, water content, slugging, foaming, solids, corrosion, operating ranges, design pressure, design temperature, retention time, extraction materials, coatings, inspection, internals, controls, safety systems, and maintenance requirements. Every blank field becomes an assumption. Every uncontrolled assumption becomes project risk. This is also where leadership matters. Oversizing is not automatically conservative. A larger vessel creates more cost, more plot space, more steel, more hazardous inventory, slower response, and sometimes poorer turndown. True conservatism means understanding uncertainty and applying margin where it protects performance. Undersizing creates the opposite risk. The savings appear during procurement, but the cost returns later through reduced throughput, compressor damage, chemical consumption, shutdowns, retrofits, and lost production. The cheapest vessel can become the most expensive bottleneck in the plant. And who owns separator performance? Process engineering defines the duty. Mechanical engineering designs the pressure boundary. The vendor designs internals. Instrumentation controls pressure and liquid inventory. Piping defines connected system behavior. Operations runs the vessel. Maintenance preserves the equipment. The lead engineer owns the interfaces. That is the real responsibility. Before you approve a separator, ask what the controlling gas case is. Ask what the controlling liquid case is. Ask what happens at minimum pressure. Ask what happens during slugging. Ask whether foam, wax, sand, corrosion, or emulsion are expected. Ask whether the internals can be inspected and replaced. Ask what happens if the level transmitter fails high or low. Ask what protects the downstream system. Ask whether the separator still works when production conditions change. Those questions often reveal more than another calculation revision. The final principle is simple. Do not simplify the problem before you understand it. A separator calculation may give you gas area, liquid volume, and vessel dimensions. Only integrated engineering tells you whether the equipment will survive the real fluid, the real operating envelope, the real upset, and the real maintenance environment. That is the difference between sizing a vessel and designing a reliable system. If this perspective connects with your project experience, like this episode, share it with your engineering network and subscribe to the channel. Tell me in the comments what separator failure you have seen in the field. Was it liquid carryover, gas blowby, slugging, foam, interface instability, corrosion, fouled internals, or a control problem that initially looked like a sizing issue? Share your technical opinion, lessons learned, and practical design principles. For more engineering design breakdowns, simplified standards, failure analysis, and project management insights, follow my LinkedIn newsletter and stay connected.